Okay, ladies and gentlemen, today we're going to talk a little bit about transformations. Just give you a quick review. Um, Transformations basically come in three categories. They can be translations, they can be reflections, and they can be stretches. Now, one of the things I want to make sure we're clear about is that all three of these things come into the category of transformation. So if you're asked about a translation, it's only going to refer to something where all the points on the graph move the same distance and direction. And if it is a reflection, then it's going to be referring to a situation where each point is the same distance but on the other side of whatever the reflection line is. And for us, it's almost always going to either be the y-axis or the x-axis. And so a stretch is when the shape of the graph is changed, either vertically or horizontally. In a translation, the shape doesn't change, it just moves. If I've got a quadratic, maybe I move it to the right and maybe I move it up, but it still looks like the same thing it did. If I do a reflection, well, then what's going to happen is that if it started out like this and I'm reflecting it over the x-axis, then it's going to look like this. If it was up here, well, then what's going to happen is that it's going to be, every point is going to be the same distance from the y or the x-axis that it was, only it's going to be on the other side. And then, of course, the other possibility is that if it was a reflection over the y-axis. So if I make this the y-axis, then if I reflected this one, it's going to be the same distance from here to here, and it'll be the same exact shape. All right? Now, a compression or a reflection stretches in Math 3, we used to refer to them as stretches and compressions. And what you're going to find in Cambridge is that we pretty much are only going to use the word stretches. So it's all about the factor and what it got stretched by. If I stretch it by a factor of 3, well, then it's going to grow vertically or horizontally. And if I stretch it by a factor of 1/2, well, then it's going to be actually what we would consider a compression, but they're just going to call it a stretch. They're all called stretches. All right? So let's keep on going. First thing is that translations often can be described using a vector. And so I want to do a quick refresher about what vector is. It's going to be set up in a situation like this where I've got two parentheses and a number are on top of each other. The important part to remember is that the top number is going to go left or right. And then the bottom number is going to go up or down. And the nice thing about this is that whatever number is in there, it is what it feels like it should be. So for example, in this case, this vector is going to shift to the right by 3. This is going to shift up by 4. So when it's positive, it goes to the right, and when it's positive down here, it goes up. So in this one, we're going to do both, where we go to the right by 1, and then we're going to go up by 2. So take a minute and try these last couple. Pause the video if you want, and then start back up again, and then we'll compare. All right, hopefully you did that. For these last two, what we're going to have is this -2 is going to shift to the left, and then this 3 is going to shift up. This -3 again is going to shift left, and this -1 is going to shift down. It's important because it's a really easy way to describe a translation, and some of the things you have to do sometimes is tell what happened, describe the transformation. And instead of writing right, left, up, down, you could just do this. In fact, when we are doing these describing of transformations, they are not going to accept the words left, right, up, or down. They're going to assume, like for example, this vector means it goes to the right. However, if you were using it in words, we would say that it is going 3 units parallel to the x or along the x. If this was here, and again, it means it's going to the left, but if I was describing it in words, what I would say is it's going -2 units along the x-axis. And again, instead of getting caught up on whether it's the right word or not word, if you're asked about a translation, the easiest way to describe it is to use vector notation, because it says everything you want it to say. You just got to be really careful, because it's really easy to mix them up. It's left or right on the top and up or down on the bottom. So now, we have situations sometimes where we've got to take and change an equation or a function based on some kind of transformation that they're given. We've got to get very comfortable with this notation. Okay? When it says this, it means, for us, it means it went up. Okay? If I were to do a vector for this, then what would happen is I would say that it went 0, 3. Okay? Now, that means it went up by 3, but they're perfectly happy with this. All right? What they're wanting to happen in this situation is they're wanting us to take this equation and change it so it shifts up by 3. And so basically, this is almost exactly telling you what you're going to do. We're going to take the function x squared plus 3x plus 1, and then we're going to add 3 to the end. What does f of x equal? F of x equals this. I just wrote it down. Now do what it says. Add 3 to the end. If I have this function, f of x equals x squared plus 3x plus 4, it is going to be 3 units higher and exactly the same shape than this original. So get really comfortable with this notation. Now what I'm going to do is take a minute, pause this, and then try doing number 2. Okay, so hopefully you did that. Again, this is really simple. What does f of x equal? It equals this. All I got to do is write this down and then minus 5 from it. So the new function is going to be x plus 3 squared and then minus 3. This is going to actually be 5 down, because I used to be at plus 2. In fact, I don't know if you remember, but this is in vertex form, right? So this vertex, what's this vertex? -3, 2. Well, this is still in vertex form. This is going to be -3, -3. All right? So clearly what's happened is it has not moved left or right, but it has gone down. And how far did it go down? Well, from 2 to -3 is 5. So anyway, that's how we do that. So let's take a look at the next one. Here, I've got a graph of a vector, only this case, you'll notice the notation is different. It's inside here. Now, when you see this, what happens is it is going to cause the graph to shift left or right. This is going to cause it to shift to the left. If there's a number inside, so if it says f of x plus 3, that's going to go to the left, 3. And if it said f of x minus 3, that's going to go to the right, 3. It's the opposite of what it feels like. Plus 3 feels like it should go to the right, but it's actually going to go to the left. All right? And this is telling us what it is we've got to do. So you'll notice I've got my function. Here it is, right here. What do they want? They want me to take each one of the x's and add 3 to it. So I start with x plus 3. Now the thing is, my original x's by themselves were squared, so my x plus 3's also have to get squared. And then I've got plus 3. Now instead of x, I'm going to put x plus 3. So now I'm going to put plus 1. And so now all I got to do is basically put all this together. What's x plus 3 squared? Well, it's going to be x squared plus 6x plus 9. And then this is going to be plus 3x plus 9, and then plus 1. And when I simplify it, I get my new and improved equation of x squared plus 9x plus 19. And then what I want to do here is, let me go over here in Desmos. Here, let me try this. Notice here where I've got Desmos, but you can't see it because it's too big. There you go. So notice here I have the original equation, that's the red one, and this is the new one we just made. It just seems kind of weird, but take a look at it. It's moved over 1, 2, 3 units. It used to be at negative 1.5, and now it's negative 4.5. It's moved to the left by 3. So where some people get kind of confused is up and down. Well, it is kind of like what you think it's going to be, but when we go left and right, it's different. So do me a favor, remember, all I got to do is do what this says. This literally says take all the x's and subtract 5 from them. So do me a favor and pause the video and then try to do this one and start back up again. All right, hopefully you did that. So again, here, this is x plus 3. They want me to put minus 5 in there. I still got to square it. And so what happens is I get this new function, which is going to be x, minus 2 plus 2. Now again, you'll notice that this is in vertex form. This vertex was negative 3, 2. This vertex is negative 2, 2. Wait, something's not quite right. Let me check this out. Oh, I see. Look here. It's minus 2. There should be a plus 2. So this is clearly moved from negative 3 to positive 2. It's going to go 5 to the right. All right? So, get comfortable with this notation. Let's take a look at this. Here, if you're given a vector and you're asked to perform that on there, basically, again, it's important that you know what's going on. Like, what's helpful is if I can change this into the function notation, well, remember, the top is left, right, and the bottom is up, down. This means it went up by 1. To do that to a function, I do this. So that means that my new function is going to be y equals 7x squared minus 7x plus 1. This one says that it's going to go to the right by 5. I know that this means I'm going to do x plus, whoops, not plus. It's going to the left by 5. It's going to the left by 5, So I'm going to do x plus 5 to make it go to the left. And then I'm just going to come over here and do what I just wrote. Basically what I wrote was add 5 to the x's. This is going to make it go 5 to the left. So if I can take this notation and then translate it into that function notation, the function notation basically tells me what it is I got to do. So pause it and try doing number 3 and number 4. Okay, awesome. Hopefully you did that. So remember, this means we're going to go to the left by 1. So that means that I'm going to do x plus 1. And then this means it's going to go up by 2. And so I take this and change it into this. And now I just do what it says. This says add 1 to every one of the x's. So it's going to be x plus 1 squared instead of just x. I'm going to think of it this way if you want. Replace every x with an x plus 1. So now it's not x, it's x plus 1. Still has to be squared. Replace this x with an x plus 1. Now, I got to add a 2 to the end. Well, so now all I got to do is clean this up. This is going to be x squared plus 2x plus 1 plus x plus 3, and that's going to give me x squared plus 3x plus 4. This is going to be this shifted to the left by 1 and up by 2. And this one, we're going to do pretty much the same thing. If I change it, it's going to look like this, function notation wise. This means I'm going to go to the right, so that means I'm going to do x minus 2. This means I'm going to go up, that means I'm going to do plus 3. And see, now all I got to do is do what it says. Wherever I see an x, replace it with an x minus 2. So 3 times x minus 2, still squared. And then this says minus 2. And then they add this plus 3 to the end. So this is going to be x squared minus 4x plus 4 all times 3, which is going to be, I'm going to go this way, 3x squared minus 12x plus 12, and then I still have to add 1, so I'm going to make this a 13. This equation is going to be what after we've done this to it, or after we've done this to it. All right, let's take a look next. Reflections. Reflections are given by this notation. Basically, it's literally what it means. Multiply the whole thing by -1. And again, notice how it says y is equal to this. So that means that this is this, right? So basically, take this entire thing, x squared plus 2x plus 1, multiply the entire thing by -1. This is equal to this. Multiply that times -1. It gives you -x squared minus 2x minus 1. This is going to be the same exact function, only it's reflected over the x-axis. So when I want to reflect over the x-axis, it's going to be in the front, and I just multiply everything by -1. Try doing number 2. Pause it, and then start back up again. Yeah, awesome. Thank you for doing that. Like I said, then this is going to be, after it's been reflected over the x-axis, is -x to the third minus 7x plus 3. If I want to reflect a function over the x-axis, multiply the entire thing by -1. All right, so now let's look over here. What about when I reflect over the y-axis? This can be a little bit more confusing, but it's basically the same premise. What you've got to do is remember that this is the notation. This is the function notation for reflecting over the y-axis. And what I'm going to do is I'm going to replace all the x's with a -1x. So let's try it. This is going to be a -x still squared. This is going to be +2, but now it's a -x and then +1. See, now -x times -x is still +x squared, and this is going to be -2x, and then this is going to be +1. Let's take a look at this. If I have this one and this one, are they really reflected over the y-axis? So if I take, let me see if I can get it over here. Hopefully you can see this. I'm not sure if you can. Hang on, let's do this instead. What I'm going to do is I'm going to stop. And now I'm going to share over here. Alright, so you'll see here that I've got the original graph. And now when I put the new one, the one we just built, you'll notice how it's reflected over the y-axis. And all I did was multiply everything times, or every x times -1. In fact, just replace every x with -x. So do me a favor and pause this, and then why don't you try doing number 2? All right, awesome. Hopefully you did that. So all I'm going to do now is rewrite this 5 plus, but I'm going to replace every x with a -x. -3 times -x still squared. And I'm going to put this in the order we're used to seeing it. So this is going to be -x times -x, which is still x squared. This is going to be -3x squared. Then this is going to be -2x, and then +5. They probably would have written it backwards. But anyway, this is going to be the same function, only reflected over the y-axis. All I got to do is take all the x's and replace them with a -x, and then multiply. Now stretches. Stretches, vertical stretches, or compressions. Again, they're not going to use the word compression. Whenever you multiply by a number bigger than 1, it's going to make it skinnier. It's going to make it thinner. If you multiply by a number between 0 and 1, it's going to make it wider. It's going to make it fatter. What we've got to make sure is we talk about when we're doing this that it's going to result in this stretch factor. Stretch factor of 2. Stretch factor of 1/2. So instead of using the word stretch or compression, that's what they're going to be doing. They're just going to be talking about the factor. If you say it's 3, they'll know it's a stretch. You say it's 1/2, they'll know it's a compression. So basically all we got to do is, like this said, if I know this notation, if I want to stretch, all I do is multiply the entire thing by, and again, there's 2 kinds of stretches. There's a vertical stretch and a horizontal stretch. Right now we're talking about a vertical stretch. So if I want to do a vertical stretch, then what I'm going to do is I'm going to multiply everything. This is what f of x is equal to. And they want me to multiply it times a. In this case, the a is going to be a 3. Because if I wrote this in this notation, it would be 3 times f of x. This is f of x. I'm multiplying it by 3. To do this, I get 3x squared plus 6x plus 3. You'd be amazed how many times people do this and they only do it to the first thing. Here's the most common one where if they had this one over here, y equals 2 times x plus 4 squared minus 6. If I want to do this stretch by a factor of 3 to this one, not only do I have to multiply this by 3, but I've got to multiply this by 3. So this is going to end up looking like this. And then it's going to be minus 18. But a very common error is for people only to multiply the first one by the 3 and not multiply everything by the 3. So the negative 6. Some of you will be, well, what about the 4? Well, keep in mind, by multiplying the 2 is being multiplied times x plus 4. So by multiplying the 2 by 3, I essentially am getting all that taken care of. Because whenever I take this power, then I'm going to multiply it by this number. It's going to be 3 times as big. It's like multiplying it by 3. However, this 6, it does need to get multiplied by 3. All right, so pause this and try stretching this by a factor of 1/2. So what that looks like is 1/2 f of x. And again, we're talking about vertical stretches right now. Pause it and then start back up again when you're ready. Okay, good. So all we're going to do here is multiply the entire thing by 1/2. This is going to be 1/2 times everything. So that's going to be 1x, or 1. It'll still be x plus 4 squared, and then minus 3. That is what we're talking about. Okay, hope that'll make sense. Let's go on. Now, a lot of this stuff we talked about in Math 3, but we did not talk about horizontal stretches. And so they're a little bit more complicated. What happens is that if I put a 3 in there, so again, you'll notice now that the number is going to be just with the x's, okay? If you remember when I did a horizontal reflection over the y-axis, that it involved just the x's. I multiplied just the x's by -1. Well, here, if I want to do this, I'm going to do it on the inside. The problem is that it's going to be the reciprocal of whatever factor I want to actually do. So, for example, if I want to change this by a factor of 3, then what I've got to do is actually do the reciprocal of that number. That's going to cause everything to shift or to grow. All the x's are going to grow by a factor of 3. So let's try this. Basically, if you'll take a look, if you look at this notation here, it basically says replace all these. So let's go ahead and do this. This is going to be not x, but 1/3 x, and it still has to be squared. And then it's plus 2. And then instead of 1/3 x plus 1. So now this is going to be 1/9 x squared. This is going to be plus 2/3 x plus 1. Y equals, and then that is going to give us a horizontal stretch. So let's take a look at these graphs. Let's see, switch gears. If you take a look over here, I've got the original function and then the new one that we made. Now, you'll see that it has not shifted up or down, and what's happening is that every x is going to be 3 times bigger. Now, take a look at the vertex. It used to be -1. Now it's 3 times bigger, and it's -3. It's true for every x. So if you go through and find a point that has a, like this has got a 1. Let's see, look. Over here it's going to be a -6, because if a y come out as a 1, the x is going to multiply by 3, and it's going to be over here. It's going to be a negative 6, 1 now. Every x is 3 times as big. But the way we made that happen was by multiplying every x by negative 1/3. And that's really confusing. So let's take a look at this one. If I'm going to do this next one, what I'm going to do is I want to change this. And again, this is a horizontal stretch. So it looks like this. I want to change it to by a factor of 1/2. I'm going to multiply every x times 2. So this is going to become y equals 2 times, not x, but 2x plus 4 minus 6. So if I want to compare these two graphs, you can see here the blue one is the original and the green one is the new one. And if you take a look at the two vertex, it used to be negative 4, but now the x is half as big, and it still matches up with the negative 6. All the y's are going to be the same, but the x that matches up with it is going to be smaller. This is going to be, whatever we get to 5, it's going to be not negative 5 or not negative 5 anymore. It's going to be half as big. It's going to be 2.5, negative 2.5, which if you take a look, it is. All right, so that's how that works. Let's go back. I don't want to forget. So, a couple of Zoll exam questions. If the graph of y equals f of x is transformed to the graph y equals 2 times f of x minus 1, describe fully the two single transformations which have been combined to give the resulting transformation. All right, so take a minute, pause this, and then see if you can't figure that out. Okay, so basically you see this number in front. That is telling you that it's been stretched by a factor of 2. This means it's been translated and it's going to go to the right. And so I'm going to go up here and I'm going to put 1, 0 because it didn't go up or down. Then I'm going to say a stretch by factor of 2. And see, this is a vertical stretch. So we're going to say along the y-axis, or we're going to say that it's a vertical stretch. Keep in mind, there are vertical stretches and horizontal stretches, so you have to make sure that you tell them which one it is so they know that you know which one's right. So take a look here. Here is the actual rubric. If you just put this down, now you could say, the problem is, like I said, if you say that it shifted to the right, I don't think they're going to give you credit. See here where it says that if you say it translates to the right, you get nothing. Okay? So what we want to say is it translates, and this is a vertical translation. So if you say it translates by 1 in the x direction, they'll take that. Or parallel to the x-axis, they'll take that. Horizontally, they'll take that. All right, but if you say it moves to the right, that's not worth anything. And then they're looking for the word stretch. And then that's worth 1 point by itself, okay? And then if you say that it's by a factor of 2 in the y direction, or if you say it's vertically or in the y-axis, then you can get the other point. This is a pretty easy 3 points. Take a look at this next one. This is part B. This is worth 2 points. The curve y equals sine 2x minus 5x is reflected in the y-axis. So it's reflected in the y-axis. Remember, that's going to be this. And then stretched by a scale factor of 1/3 in the x direction. That's a horizontal okay, in the x direction is horizontal. The x-axis goes horizontal. So that means that we're going to, well, you tell me. Pause this, and then you tell me what it's going to be. Okay, so hopefully you did that. So keep in mind, we got a couple different things going on here. We're going to reflect it in the y-axis. That means we're going to do this. So let's start with that. Y equals sine. Now we're going to take, and then this is not going to, this is going to be 2 times negative x, or negative 2x, okay? And then what we're going to do is minus 5x, but that's going to be a negative x, so it turns out to be 5 times, negative 5 times negative x, it'll be plus 5x. And then it says that we're going to stretch it by a scale factor of 1/3, so it's horizontal, so that means we're going to multiply every x by 3. So now this is going to be negative 6x, and then this is going to be plus 15x. So let's take a look and see what the answer thing says. So they give you both of these choices here. Negative 6 sine negative 6x plus 15x. That's what I put down. All right, now notice they're going to give you 1 point for this, and they're going to give you 1 point for this. So if you got this right, you get a point. If you got this right, you get a point. If you get them both right, you get both points. Okay? And then that's all there is points for this one. Okay? All right, take a look at here. It says functions f and g are both defined, all real numbers, and are given by blah, 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 blah. They're both quadratics, clearly. First, by expressing both f of x and g of x in complete the square form. Complete the square form, we would say, is vertex form. Express g of x in the form of this. Now this is that notation. F of x plus a number plus q. So basically what they want to know is they want to know what happened to f of x. Left and right, up and down. So first, put them both in the vertex form. Pause this, and then start back up again when you're ready, and we'll check them out. Okay, so let's try this one at a time. If you take this and put this in a calculator, you can find the vertex, okay? I believe the vertex is going to be 1, 4. Negative 2, so it's negative b over 2. That's going to be 1. Put it in there. All right, so this vertex is going to be 1, 4. If you put this in your calculator and then use the quadratic, solving thing, you can find that this vertex is going to be negative 2, 9. So if I'm going to write these in vertex form, f of x is going to look like this. X minus 1 squared plus 4. G of x is going to look like this. x plus 2 squared plus 9. All right, now, what they want to know, that's part A, what they want to know is this, though. So what they want us to do is tell what's happened, left or right, from F to G. So basically what we're going to say is that it says describe fully what turns the y of f of x to this g of x. All right? So f, and then what's going to happen is that it went from -1 to +2. So that means we must have added 3 to this -1 to get it to +2. Then we went from 4 to 9. So we must have plussed 5. Okay? So let's see what they were given points for. They give you a point for each one of the correct ones and situated. This is worth 4 points? Oh my gosh. So they give you a point for getting this right and then getting this right. If you put it in vertex form, you're getting 2 points. And then x plus 3, -1 to 2 is +3, 4 to 5. Like I said, they're talking about that notation there. And then it says, describe fully the transformation which transforms this to that. So what exactly happened from here, from f of x to g of x? What happened from this to that? Pause it and jot it down and then start back up again. Okay, hopefully you did that and see, obviously this is obviously a translation. I mean, we've seen it, right? This is going to move to the left, it's going to move to the right or up and down. All we got to do is put down this in vector form and it will accept it. You can separate them, but this is what happened. It went left by 3 and it went up by 5. All right, let's take a look at this. Here, I've got a function. It says the diagram shows me f of x. That's this guy right here. And it says that where it is, so this is this graph right here. All right. State the range. Okay, so we might as well go ahead and do this. Keep in mind, this is the midline. So the midline is going to be 1/2. This is the amplitude. That means this, from here to here, is going to be 1.5. So that makes this number a 2. This is 1/2. It's going to be down by 1.5. So that makes this a -1. So the range is going to be from -1. Oops, I guess we're doing brackets. -1 to 2, right? So now what it says is that a function g is such that g of x is equal to f of x plus k. So what they're saying is I've got a new function, but the way it's going to be the same as this old function plus a number. Now, it says my new function is tangent to the x-axis. So it's basically the same as the function I was looking at, only it's plus a number. Well, if this is going to have to be touching the x-axis, and it's at -1 right now, then that k must be a +1. Let's take a look and see what it says. Yeah, k's got to be a +1. And then, oh, does it ask this? It says, then describe the transformation. Well, again, this is going to move it 1 vertically, parallel to the x-axis. All right? Translation of 1. Now, again, like I tell you, it seems weird, and now they're okay with up. but 1 unit parallel to the y-axis. Make sure I would definitely put the parallel to the y-axis. All right, what else we got here? C, oh, another part. Now it says, state the equation of the curve, which is a reflection of f of x. Now, over the x-axis. So remember, if I want to reflect it over the x-axis, it's going to be this. Take the whole thing and multiply it by -1. So I'm going to take this whole thing, 3 over 2 cosine 2x plus 1/2. Now, this is the part that messes people up. This is totally going to get multiplied by -1. But it's -3/2 cosine 2x. This is all together. This is one thing. I'm not going to be multiplying that 2 times -1. All right? This is going to get multiplied by -1. And so then it just becomes -1/2. Both of these two things have to get multiplied by -1 to reflect over the x-axis. So let's see what it says. -3/2 cosine 2x minus 1/2. Right? Pretty simple point. Pretty easy. It's not going to cost them very long, but you got to reflect over the x-axis. And see here, even in the terminology here, they're trying to let you know, don't multiply this by -1. Only this and this have to change. They're practically telling you not to change this, but people love to do that. Okay? What we got here? F and G functions. Okay, state the ranges of these two functions. And then it says we've got this. So first, again, let's do the same kind of logic here. This is the midline. It's at 2. This is going to be the amplitude. It's at 3. So that means that the highest point has got to be 5, and the lowest point has got to be -1. All right. So my highest and my lowest, okay? So that's the range for f of x. F of x is going to be between less than or equal to 5 and between that and -1. That's f of x. Okay, now take a look what they did to g of x. What they've done is they've multiplied it by 2 and then they've reflected it. So what's going to happen is that this is going to be up here and this is going to be down here and then it's going to be times 2. So now, I'm not sure that makes sense. Let's take a look at that. Oh, I see. We're multiplied by -2. So this is going to be a 2. -1 times -2 is going to be 2. And this is going to be -10. Now that makes sense because my bottom number has to be lower, right? So then g of x is less than or equal to 2 and greater than or equal to -10. All right, now, in the next part, it says that we're doing this. This means it's going to shift to the left by pi, okay? So we're going to say, and again, it's a horizontal shift. So let's say, describe fully what goes on from f of x to h of x. So we start with this, and then we do this, okay? And we can't forget this. So first, we got a reflection over the x-axis. Then we got a stretch, a vertical stretch by a factor of 2. That takes care of both of these. Now we've done this third thing, and this third thing is going to be a horizontal we'll say we'll say pi, horizontal, along x-axis. I'm not sure about this. Let's take a look and see what they say. Alright, we got that. Reflects over the x-axis, stretch factor of 2, both those are a point. Oh, we could have used vectors, yeah, right. Okay, now again, notice how that says that it goes to, whoops, in the negative pi direction. Oh, you're right, it is negative pi, isn't it? Negative pi, right? Now, they got this backwards, I think, because left, right, up, down. But anyway, that's what's going on there. All right, one last one. Here, we've got this solid one, and then we've turned it into the dotted one. State in terms of f what's happened. All right, so pause it and tell me if you think, well, you know what happened. Okay, hopefully you did that. So take a look. It didn't just shift to the left because the shape is different. So take a look at this point here. It's 1 away from 2, and this one is 1 away, well, not 2, but from this y-axis, okay? This point is 2 away, this point is 2 away. This is a reflection over the y-axis. And how do we say that? Well, we say it like this. That's a reflection over the y-axis. And I think that's all pretty much they're going to accept, because they're saying specifically they want it in terms of f. So tell me about this one then. What's happened here? Pause it, jot it down. What happened from solid to dotted? So again, this can't be a translation because the shape is not the same. It's not a reflection because we're not over the y-axis or the x-axis. So this must mean there must be some kind of stretch. So let's take a look at these values here. This y used to be a 2, and now it's a 4. This y used to be a 1, and now it's a 2. This y used to be a 3, and now it's a 6. It looks like we're stretching vertically on the y, and it looks like that we're multiplying by 2. So that's a vertical stretch. And again, that's all they're going to take. What about this? Pause it, tell you what this is going on here. Remember, we're starting from solid and going to dotted. All right, so let's take a look here. It's not a reflection over the y-axis or the x-axis. The shape is the same identically, so that means it's not been a stretch. So that means we're talking about a translation, left, right, up, down. So let's just pick this one point. This one point went 1, 2, 3, 4 to the left. X plus 4, that's going to make it go to the left. Then it went down 1, 2, 3, minus 3. And the thing is, if you check, every point does the exact same thing. 1, 2, whoops, did I count this wrong? Let's try this again. 1, 2, 3, and 1, 2, oh wait, that's all the way over there. Duh. Ha! 1, 2, 3, 4. Yeah, it's going 4 to the left. This one's going 1, 2, 3, 4. And then it goes down. 1, 2, 3. Each one of these points, they all do exactly the same thing. They go left 4 and they go down 3. This is worth 2 points. I'm guessing you're probably going to get 1 point for this and 1 point for that. Yeah, that's what they're looking for. 1 for this, 1 for that. 2 points. All right. That's all I've got for you today. I appreciate you watching. I hope this helps, and have an awesome day.